And welcome back, everyone, to Environmental Sciences 347, Climatology. Now we're going to get into anthropogenic or human climate change. Remember, anthropogenic is just a fancy word meaning man-made, human-caused, whatever framing you want to put on it. But that's what we're looking at this time. We've already looked at natural climate change, what changes climate in the past naturally over much longer time frames compared to what are we doing to the atmosphere and the entire climate system now. So, what is the impact of human activities on the global and local climates? We could actually do an entire course just on this, but we will hit the highlights for what you need to know before you leave out of this class. So first of all, don't let anybody tell you this isn't happening because they're either ignorant or lying. There is very strong scientific evidence throughout all global scientific communities that climate change is happening. Global warming is happening. Basically, what humans are doing by burning fossil fuels and putting greenhouse gases into the atmosphere is in the net warming the planet, especially over these last 40 to 50 years. The United States Global Change Research Program, the U.S. National Academy of Sciences, the American Geophysical Union, and not pictured here, my personal favorite organization, the American Meteorological Society. So there's really no question about this. Anytime somebody tells you otherwise, for some reason they just don't want to believe it, for whatever reason that may be. You've probably heard of the IPCC. Who are they? The IPCC is the Intergovernmental Panel on Climate Change. This was established back in the late 80s to provide policymakers with regular scientific assessments on the current state of the science about climate change. The IPCC isn't doing any research. It doesn't monitor the climate-related data or parameters. They're not telling people what to do. They are collecting information and providing it to policymakers, heads of state, whatever. There are thousands of scientists from all over the world contributing to the reports, all right? But there's no IPCC over here doing research. They're putting together the research from other laboratories and presenting it to policymakers. And this is done periodically on the course of about every 6 or 7 years. The 6th report is actually coming due soon, but this is an essential part of this process to ensure an objective and complete assessment of the current state of scientific information. Where do they come from? Well, they aim to reflect a range of views globally, supported by the WMO, which is the World Meteorological Organization, that's a division in the United Nations, and the United Nations Environmental Program. All right, so this is basically UN stuff, but don't let that scare you off. All right, it is hosted at the WMO headquarters in Geneva, Switzerland. So this is basically the authority, as it were. It's not perfect because anytime you have thousands of people getting together, little things will slip, all right? But this is pretty good stuff. The IPCC reports come down to 3 basic working groups: the physical science basis, which is the core science of climate change, and then kind of what we do about it, the impacts, the adaptation, and the vulnerabilities that we have, and then mitigation. Then what happens? What do we do about it? How do we deal with it? All right. The last assessment report came out in 2013, and the next one is actually in process. The first wave of the reports are due, and I typed in 2020. I meant 2022. Comes out this year and continues into 2022. So one of the things we have to do is examine what are the pluses and the minuses of the radiative forcing, both internally and externally, to the global climate system. What are things that are forcing the system in one direction or the other that we can measure and that or we can even estimate? All right, so these are the things that we put together. And ultimately it comes down to this chart from the IPCC. And it's pretty messy, sure, but this is kind of the state of the science. We look at long-lived greenhouse gases, things that stay in the atmosphere a long time, then relatively shorter ones, ozone, whether it's in the stratosphere or in the troposphere, how the surface albedo has changed with land use, and then total aerosols. In other words, when we burn other stuff, soot, um, other sulfate particles, all that stuff going into the air as well. Contrails, when airplanes fly, they leave behind the condensation trails, which are basically just clouds, right? And then any kind of change in incoming solar irradiance, all right, which really hasn't been that much. When you add these things together, and you see these little bars in between the lines at the end of each bar, at the end of each color bar, those are error bars. We don't know it to a super duper precise level, but we have a very good idea, and that gives you a range of uncertainty. So when you do the summation of all of these radiative forcing components, all right, it adds up to a net positive radiative forcing or a warming, all right, about 1.5 watts per every square meter of the Earth. All right, you think about a 100-watt light bulb, 1 watt isn't that much over a square meter, but you add that over the entire planet, and it does add up. So the total net anthropogenic, the best guess, is about 1.5 watts per square meter. But you look at that bar, the little black line that goes from the end of the bar into the middle. The best guess is 1.5, but the most likely range is somewhere between 0.5 and 2.5. All right, so that's a pretty wide range. And this is why there is so much uncertainty as to how much warming is going to continue. Without question, the planet is going to continue to warm. How fast, how intense is still open for some debate, but everybody knows that it is warming. Some places are going to warm more than others. Some places are going to warm less than others, but everybody is going to warm. When we look at some of the individual components of that graph and we think back to aerosols, and aerosols is a funny word because I still remember the 70s as a kid hearing that word and thinking about spray cans. But aerosols are any particulate matter that's suspended in the atmosphere, any kind of teeny tiny chunk of pollution that's just hanging in the atmosphere. Sulfate particles, dust, soot, anything is just hanging up there, right? And for most of the mid-20th century, there were a lot of aerosols up in the atmosphere just from all the post-World War II industrialization and everybody kind of rebuilding society after World War II, okay? Now, knowing that most of the land on the planet is in the northern hemisphere versus the southern hemisphere, it probably doesn't shock you that 90% of any anthropogenic aerosols are byproducts of fossil fuel burning in the northern hemisphere. Right now, generally, they can have a cooling or a warming effect depending on the type of aerosols. Sulfuric aerosols or sulfurous aerosols can do the cooling, but then you can have black carbon, which can do warming. So these can work in either directions depending on exactly what their components are. And again, these can also alter the number or the size or distribution of cloud droplets. Remember, you've got to have some impurities in the atmosphere anyway to get water droplets to form higher up into the atmosphere. Remember, you get super cooled water. All right, you need to have something for your water vapor molecule to condense around. So if you got a lot more aerosols up there, you got a lot more, as one of my professors said in the 80s, crud in the atmosphere for your water droplets to form. All right, so aerosols in the atmosphere have an impact on the size distribution of cloud droplets and then ultimately into rainfall. This is why you hear some of this weather modification stuff about people throwing silver iodide into clouds, hoping rain is going to form. And they do provide these cloud condensation nuclei, but it's really not enough to make a genuine rainstorm. We just do not have the technology, we do not have the materials to fundamentally and largely change individual weather systems that are on the scale of a couple of states. All right? That's just not going to happen unless we figure out something amazing in the next few decades. What we're doing to the atmosphere isn't controlling the weather. We're controlling the background conditions of the entire planet. And then the weather changes based on what we've done to the entire large scale system. So I kind of get ticked off when somebody says, well, we can't change the weather. Well, no, we're not changing the weather, but we're changing the global climate system. And then that in turn impacts the weather that occurs. So we think further about changes in land use and land cover. Of course, human development has transformed about a third, to some estimates about a half of Earth's land surface. All right, think about North America. There's so much forest east of the front range of east of the Mississippi River. Front range of the Rockies is more like plains and stuff. All right, but think about all the cities that have developed. Think about all the cities in Western Europe. All right, think about the big cities in Southeast Asia. This affects the vertical flux, or that transfer of heat and moisture from the ground to the atmosphere. This changes where thunderstorms can occur and may even impact atmospheric and ocean circulations. So that in mid-latitudes, where we do have a very high population, let's say between the Tropic of Cancer and the Arctic Circle, where a lot of people live, all right, the clearing of forest for agriculture and then reforestation of abandoned farmland has caused regional climate change. We've got changes in the long-term temperature patterns in local areas because of change in surface conditions. Whether you've cleared forest, you've built an airport, you've built a city, or you've reforested an area that had been cleared out. There's not a lot of virgin forest left in the eastern United States. We cleared a lot of it at the end of the 19th and early 20th century. A lot of it has actually been reforested. So when we think about anthropogenic versus natural forcing of climate, we can drop this into two buckets. There's the positive forcings, which are causing the climate to become warmer. And then there's the negative forcings, which cause the climate to become cooler. All right, so greenhouse gas is generally a positive, and in the net, the aerosols cause the climate to become a little cooler. Yes, you have a few aerosols that are positive, but in the net, all the aerosols tend to cause the climate to cool. So then the net radiative forcing of all of that, and that is anthropogenic in origin. All right, so this is where we step back and go, well, we know we've got this forcing and this forcing and this forcing and land use and ice and aerosols and CO2 and methane. And then we use the global climate models to predict the future. All right. The problem is, even today, we still don't have a very strong way to simulate the impact of clouds, and to a second degree, aerosols. We've got an okay handle on it, but we don't have the best handle on it. We've got enough of a handle on it to realize that they are going to make an impact, but they're probably not going to impact enough to cool the planet. The big question is, how fast are we going to warm? Talk about, we don't know how fast we're going to warm. It depends on how much CO2 we put into the atmosphere next 20 or 30 years, and it depends on what kind of cloud cover forms. Is that going to be a positive or a negative feedback? We do not see a situation setting up where enough cloud cover forms in the next 20 or 30 years to balance or to counteract the increase in positive forcing in greenhouse gases. All right, it might slow things down, but I wouldn't gamble on that. So then we have to talk about the climate models. And I've mentioned this at the outset because there is so much consternation about the climate models, all right? The climate models are tools. A model is a tool. It is not something you just look at and go, well, that's the future. No. You have to understand certain things and certain imperfections about the model. But the model will still, in most cases, have skill. It will tell you something more than what you knew before. All right, that's Gavin Schmidt, and I said before, go watch his TED Talk. Again, it's 7 years old, but it's still very strong. All right, there's a link. You can just Google Gavin Schmidt TED 2014. That's the title. And remember this, a model result has skill if it gives better predictions than a simpler alternative. In other words, you just roll out of bed and think, well, I think the climate's going to do this in 15 years. Then you go back and look at the climate model. What did that say 15 years ago? Has it happened? How much of it has happened? How close is it to happening? This is what we mean by model skill. Is it telling you something you didn't already know? Is it giving you an insight that you didn't already have? It's not yes or no, but does it nudge you towards a solution that tells you something more beforehand? And that's what it's all about. So these numerical simulations are designed so that certain known fundamental variables can be changed and then see how the system reacts. All right, so we can tweak the amount of CO2, we can tweak the amount of methane in the model, we can change land use in certain locations. We do experiments with the model to see how the model responds. And these are the things that will help guide us into making decisions down the road, right? The models are always getting better. As our understanding of the climate system improves, we're able to better simulate it. But it isn't just being able to simulate it. Then it's about getting the computer simulation, the computer computational power to run these simulations because they're so complicated. All right, the amount of code in these things is absolutely phenomenal, which is why you have to run these on supercomputers, which will do more than a quadrillion calculations in a second. But you can't just run the thing in a couple hours and get a result. These things take hours to days to come to a conclusion, and sometimes even longer than that. So a little bit, here's a couple of examples that are a little bit older, but the graphics here are kind of telling. On the top, this is an average of several different models and simulations, okay, where we look at the observed temperature in black and then the model temperature in red. All right, so we've got a good handle on the observed temperature. Again, this is the global average temperature. All right, and then we take the conditions as we understood them at the end of the 19th century. And then we throw those into the climate models. 58 different simulations. Again, because we don't know everything. We don't have one perfect simulation. We have to make some guesses. And different labs across the country are going to make different guesses. Whether they're, an organization in Australia, different government organizations in Europe, South America, Asia, they're all doing their own studies. All right, so then everybody kind of looks at all the data and sees what kind of trends fall out of that data. All right, so looking at that and getting the modeled average, you see that those two curves are reasonably well put together with the global average temperature there, the anomaly from the 1900 to 1950 average shown there. All right, then on the bottom, we do the same thing. We have a few smaller number of simulations, all right, because not every, you can't, again, every simulation is built a little bit differently. So there's 19 different simulations used here. Same temperature curve is in black, just like in the top frame, all right? But in this particular case, these models, simulations, were allowed to remove the anthropogenic forcing, took out the climate, took out the greenhouse gases, took those things out of the model, and then ran the model again. And then you get the blue curve on the bottom, which is much like we saw a couple of lectures ago with the solar output. All right, the curves begin to diverge around 1970 or certainly by 1980. All right, if there weren't greenhouse gases in the atmosphere, the planet would not be as warm as it is right now. It would be much more like it was back in the 50s and the 60s. Winters here would be colder, like they were in the 60s and 70s. All right. Just about everybody watching this who's enrolled in the course has never experienced a record cold year. Just haven't. All right. That's a big, big difference. And again, those temperatures are in degrees Celsius, not even Fahrenheit. Remember, for about 1 degree of Celsius is 1.8 degrees Fahrenheit. So 2C is it's about 3.5 Fahrenheit, 3.6. All right. So it is significant. 1 degree over an entire globe is a lot of energy. So going forward in time from present day, let's say about 2020 or so, how much more warming happens depends on a lot of the decisions that are being made right now. Whether you have a high emission scenario or a low emission scenario. Fortunately, a lot of the highest or worst case scenarios looking like they're going to become less and less likely. That RCP, representative concentrated pathway 8.5, which means 8.5 watts per square meter. That's looking less and less likely as we're starting to see renewable energy beginning to scale up across the world. It's still got a long, long way to go, but we're starting to see that scale up. Still a lot of natural gas, still a lot of oil, and certainly coal still being used. But coal has taken a nosedive in the last 10 years or so. But this gives you an idea of kind of the scenarios, the kinds of ballparks we'll be playing in the coming 30 to 70 years. Right? We've already seen the global average temperature come up about a degree and a half Celsius since the Industrial Revolution, or since the early industrial era. Let's call that the late 19th century. So how much more is it going to jump? Likely depends on the decisions we make here in these next 20 to 30 years. Again, what you see on the left is degrees Celsius, not Fahrenheit. All right, if it's 2 degrees C, that's about 3.5 Fahrenheit. So 4C, it's about 7 Fahrenheit. Remember what I talked about in the last lecture? When we had the last ice age, the planet was only about 10 degrees Fahrenheit colder. So we're talking about a big, big league warming taking shape. So with that also comes rising seas, rising sea level, coastal flooding, that kind of thing. Because when you bring that temperature up, you're going to melt land ice. You're going to melt more off of Greenland. You're going to melt more glaciers. You're going to melt more off of Antarctica. You're going to have ice shelves beginning to break up. Again, the whole thing doesn't melt away in 20 or 30 years. It's not going to happen like that. All right, but enough of it will happen where we could see a significant change in sea levels, depending on how fast the warming takes shape. Because the ice dynamics are still something that is being studied very closely, especially in Antarctica, because there is just so much ice in Antarctica. But in an extreme scenario, by the year 2100, you're looking at 2.5 meters of sea level rise. That's 7 or 8 feet. All right, think about 7 or 8 extra feet of water at the shore, at the beach, all the time. All right. Hopefully, it doesn't get that bad. That's the extreme scenario. But this gives you a range of possibilities. Anywhere between 1 and 8 feet. That's a big range, but it's not like it's going to be 30, and it's going to be more than just a couple inches. So this gives you a ballpark estimate of what you should expect. This is the range of possibilities coming down the way in the next 70 to 75 years. So we tried to go back and look at analogies for this situation in the past. That's why we have geologists. That's why we do these paleoclimate studies. Can we find any time in Earth's past where there's been this type of rapid increase in carbon dioxide? And really, it just hasn't. All right. We look to identify various factors that might have contributed to such fluctuations, but we just haven't had any luck. The search for realistic analogs just has not been successful because we just haven't seen something like this happen in Earth's past. Now, again, as I mentioned way earlier in the course, it has been a lot warmer in Earth's past before. It has been a good 10, 12 degrees warmer in the distant past. The Paleocene, Eocene thermal maximum, but the continents were in a different configuration. There was a lot more carbon dioxide in the atmosphere, and this was right after the dinosaurs, and then the particulate matter, the dust and soot and all that stuff settled back out of the atmosphere. So 56 to about 40 million years ago was when it was the warmest. All right, but this is a very, very, very long time ago. We had no cities. We certainly didn't have modern humans. So it was a very different planet that far back. In fact, when we talked about the Milankovitch cycles, the orbital cycles, the tilt of the Earth on its axis, how that varies, the eccentricity of the Earth's orbit, that all suggests that we should be heading back to Ice Age conditions. But given what we're doing with the greenhouse gases by the burning of fossil fuels, the greenhouse gas forces are very likely going to override that. But do also understand that the oceans play a large role in climate prediction because they do take in so much energy. It takes a lot more energy to raise the temperature of water than it does to raise the temperature of land. But because we do continue to put carbon dioxide and other greenhouse gases into the atmosphere, the global radiation budget's not in equilibrium. If things were in equilibrium, we have about the same number of record highs versus record lows, and that's just not the case. We are rapidly outpacing that. More record highs are being set, almost 2 to 1 globally, as the planet continues to heat up. So more about sea ice and ultimately sea level and those impacts. The geological evidence shows that there have been times when sea level was way, way lower than present. We've got offshore drowned beaches, we've got submerged river valleys, submarine canyons, so the sea level has been a lot lower at present. All right, if you think about when we did have the Ice Age, a lot of the water was locked up in glacial ice across North America and Asia. So if all that water is locked up in glaciers in North America and Asia, that means the ocean level dropped. Right? So once those glaciers melted off into the ocean, sea level rose again. Right? So there was a time the Mediterranean Sea was a great big Mediterranean dark dry valley. But as we came out of the last glacial maximum, that's when we started to see sea level rise. So the persistence of the current global warming trend is likely going to cause sea level to rise and melting of polar ice sheets and mountain glaciers and cause a thermal expansion of water. So again, the sea level is coming up for 2 reasons. One, you're melting land ice, Greenland, glaciers, Antarctica. You melt that off and it goes into the ocean. Remember, sea ice that comes and goes every year, that doesn't contribute to sea level rise. But land ice that melts and is done going to the ocean raises sea level. That's one. Two, the fact that you're just warming the ocean to begin with, raising the temperature of the ocean, like most everything else, a substance will expand when heated. So it's those 2 things together, thermal expansion and melting of land ice into the oceans, that are bringing sea levels up. There is still an awful lot of glacial ice out there. Right? About 90% of all the planet's glacial ice is still covering Antarctica. And if that whole thing were to melt, then again, that's not going to happen in your lifetime, not going to happen in my lifetime. It's going to take a very, very long time, if that happens at all. It's really, really cold down there. All right, but the point is, we do see melting taking place. When we say rapid melting, we mean rapid in the course of geological time frames. All right, it's not like the whole thing melts off in a week. All right, but in the scope of geological time, the melting is fairly rapid. So the ice shelves, the glaciers in Antarctica have lost mass and continue to lose mass. Then we think about, let's go back to the northern hemisphere in Greenland. During the summer, there's always some melt taking shape during the summer, and then everything freezes back up over the winter. But what we're starting to see now in Greenland is that we're getting these larger meltwater lakes that form on the surface of the Greenland ice sheet. Right? And just like we get potholes forming in pavement during the spring as stuff freezes and expands, the same situation is happening here in Greenland. You get cracks in the glacial ice, then you get some warming, and you get a little melting on the surface, and then that starts to run down into the cracks and form these big crevasses, allowing water to drain all the way down to the base of the glacier. And we've reached a point now where winter snowfall is not sufficient to offset the summer melting anymore. So the Greenland ice sheet is slowly melting away. I say slowly melting away. It would take hundreds of years still to melt away. All right, it doesn't happen in your lifetime, doesn't happen in my lifetime. But there is a net melting of the ice sheet. Remember, it's thousands of feet thick. So it's not going to all melt and run into the ocean next week. All right. But there is a net loss of ice mass on that glacier. Then coming back to more temperate glaciers, let's say in Montana's Glacier National Park, seen here, there's, the running joke is that you're going to have to rename Glacier National Park in another 30 or 40 years because there aren't going to be any glaciers left. If you go back from 1938 to 2006, you could see the retreat of that glacier in Glacier National Park. Because remember, a glacier is a very, very slow moving mass of ice. It's not static, all right? But the glacier retreats as it warms. So you're still having that flowing of ice, but just the end of that flow becomes more liquid, starts to form a lake, because you've got a net warming going on over the course of a year. This will in turn lead to that greater sea level rise we talked about. All right, so the thermal expansion of warming is probably going to be a greater contributor to the average sea level rise more than the melting of the land-based glaciers in this century. All right, not by a lot, but right now it looks like thermal expansion outpaces glacial melt when we look at the entire component of sea level rise. But do remember that when we think about sea level rise, it isn't just, oh, the beaches are going away. Remember that it's all kind of connected. There will likely be more flooding on inland bays than there will be on ocean fronts. Right? If you think about Virginia Beach and all the inland bays there, if you think about the Pamlico or the Albemarle Sound on the Outer Banks, if you think about all the inlets of the New Jersey shore, those things are going to flood too, because it's all connected to the ocean, right? So you're going to have flooding and you're going to have recurring flooding there. It's not all just, you're not going to just wake up and it's all flooded in a year from now. It takes time. It's tidal. And in time, your tidal flooding, your coastal flooding from repeated storms gets so bad that people just not going to want to live there anymore. All right? Property values will drop. People will tend to leave. So again, it's not one of these things you just wake up and it's horrible. It's going to be gradual in the terms or the time span of a human life. But in geological time frames, it's rather fast. You've probably heard the term polar amplification or Arctic amplification. That means that the Arctic is warming faster than the rest of the world. Estimates are between 2 and 3 times faster than the rest of the world. Cold things warm more easily than things that are already warm. Cover that earlier on in the course. All right. There's a lot of ocean in the Arctic. The Antarctic is land. It's easier to stay colder. Ocean is going to warm more quickly. All right. And with a lot of the land in Alaska and Siberia, in the Arctic, with the warming that has taken place, a lot of the permafrost has been up there for a very, very long time is starting to melt. And when that permafrost starts to melt, you get these thermokarst lakes, which is what you see on the screen there. You've kind of got this it looks like there's moss kind of covering the ground, right? The permafrost melts and you get these pools that just show up. Right? And this is a big source of methane. Methane is another important greenhouse gas. Right? Again, it settles out of the atmosphere, but if the sources of methane outweigh the sinks, you're going to still have a big net warming. When we look at the Arctic sea ice extent, again, this in of itself does not contribute to sea level rise, but it's a good barometer or a good way to measure or get a hold of the idea of how fast that part of the globe is warming. The satellite records go back to 1979. Before that, you've got a lot of ship reports. All right, that's why you see a lot more variation and that time before 1979 because the reports weren't quite as accurate. But one of the things we have noticed, even though there have been some up and downs from 1953 to about 1983, after 1983, we started seeing a drop. And that drop became a lot more precipitous, if you will, in the 90s and continues to this day. And as we mentioned in previous lectures, we do not have the amount of multi-year ice left in the Arctic Ocean. Most of the ice that's in the Arctic Ocean forms during the winter and then melts away. There's a little bit of ice that's left up there that survives the summer season. Okay, the Arctic is not ice-free in June and July, at least not yet. But we are unquestionably on the way to having a seasonally, briefly ice-free Arctic, probably in 20 or 30 years from now. We already, just in the past decade, have been able to see ships navigate the Arctic with not a lot of difficulty during the summer because the ice just isn't as thick. And that's only going to continue. And that has geopolitical ramifications. If you think about the large Arctic coast in Russia. So what does this mean for the biggest natural heat engines on the planet, hurricanes? Remember, hurricanes is the Atlantic name for tropical cyclones. These are warm core storms. So thinking about hurricanes and the water cycle, remember that because we're warming the planet, we're setting the water cycle up to run on a higher octane fuel. The evaporation, condensation, precipitation, that's all happening more rapidly as there's more energy into the system. All right? Because tropical cyclones really and ultimately are deriving their energy from the evaporation of seawater, the whole latent heat release thing, you would think, okay, well, that's going to clearly play a role in the formation of hurricanes. But it's only one thing that gets tropical cyclones to form. Once they do form, you've got more energy for them, but you have to have other conditions in play first to get tropical cyclones to form in the first place. You can't just have warm water and that's it. You've got to have moisture in the middle levels of the atmosphere, 5 to 15,000 feet. You don't want it too dry there. You also talked about you need to be farther away from the equator. And in the Atlantic specifically, the Atlantic is susceptible to having these big areas of Saharan dust coming off the African coastline. So all of these things together play a big role in having tropical cyclones form in the first place. But once they do develop, there is more energy for them to sustain themselves and therefore get stronger. This graphic is based on a paper that actually came out in 2020 that shows the percentage of all hurricanes as major storms is tending upward. That doesn't mean that they're all getting stronger all the time, but the percentage of all hurricanes that are out there spending their time as major storms is tending to be on the increase. So you could kind of say, okay, well, they're tending to get stronger, which is consistent with what we know about warming oceans, because the oceans have certainly warmed within the past century, and especially in the last 50 to 60 years. So there's evidence that the hurricanes are starting to tend a little bit stronger. But having said that, going back to what I said before, they've got to form first. Right? So we don't necessarily see more hurricanes in a warming world, but stronger ones once they do form. And what does that mean? It means when they do form, the storm surge can be higher, meaning the coastal flooding that comes with them. The rainfall can be heavier. Like those two things are pretty much locked in and they're already occurring. And there is early evidence to show that they are moving more slowly. And if they move more slowly, they're going to put down heavier rain over one spot. And then they might be intensifying more rapidly, more quickly. This term rapid intensification, where it goes from, let's say, a category 1 to category 3 in 24 hours. With warming ocean water, there are signs that that kind of thing could be happening more frequently, which makes it more of a threat to coastal locations. If you're getting ready for a hurricane coming into the Gulf Coast, you think, well, okay, we got everything ready. We think it's going to be a Cat 1, and then you're ready for it, and you hunker down, you think it's okay, and you wake up the next morning, oh crap, it's Cat 3. That's a different beast. All right. With the intensity of the water cycle ratcheting up, it means a couple of general things. The higher global temperature can mean more severe drought in places that tend to be dry, and it can be wetter in places that are already kind of wet. So the short version, wet places, humid climates will tend to actually get wetter. Deserts will tend to get drier and probably expand a little bit, right? So that's the overarching theme. It doesn't work that way everywhere all the time. But when we're trying to think about what does a warming world with a more intense water cycle mean, it intensifies what's already out there. Wet places are wetter, dry places are drier. While we're still thinking about the oceans, we also then think about marine life, right? And what does that mean? Because, a lot of the world gets a lot of its protein on things from marine life, all right? Warming can raise the sea surface temperature sufficiently to, first of all, threaten coral reefs. And if it rises too rapidly, the reefs aren't going to be able to grow fast enough, they're going to die. We've already seen a lot of coral bleaching, especially along the Great Barrier Reef in Australia. Organisms are very vulnerable to environmental changes that affects them, right? Gradual changes can be handled by marine ecosystems, but what we're doing is just too fast. This is part of the reason why we're starting to see fish show up in places that didn't show up before. This is why it's getting harder to get lobster in New England. Fish are migrating into different places, into temperatures that are more suitable for them. And in turn, this can mean more food security issues. All right, so there's the marine life to be sure. All right, shrimp, scallops, fish, da 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 da. But we also have to think about there are countries that are unlike the United States, which just aren't as developed, and they are much more dependent on agricultural as their way of life. So they are much more vulnerable to the adverse effects of warming and climate change, more likely to experience a decline in food production. So there's, the risk of, I don't want to say mass starvation, that's overselling it, but food security and decreased economic prosperity in places that already struggle day to day. We like to think, well, natural disasters affect everybody equally. The actuality, they don't. People who don't have a lot to begin with have a lot harder time to recover after a natural disaster. In fact, some people don't even want to call them natural disasters anymore. And that's fine. Call them environmental disasters if you like. In the oceans, because so much of the carbon dioxide that we're putting into the atmosphere also gets dissolved into the ocean, almost half of it, the water is turning more acidic. I mean, it's not turning into battery acid, all right, but the acidity of the water, all right, is increasing. the pH is dropping. All right, and the pH of that water is very important for marine organisms who are making shells out of calcium carbonate. So if you've got more carbonic acid, all right, your water is becoming more acidic. It is going to be more difficult for these organisms to build shells, calcium carbonate shells, because their water is more acidic. So it's going to be tougher on them, and as a result, they're not going to survive as much. This gives you kind of an idea. The CO2 that's absorbed by the ocean participates in those chemical reactions that increase the acidity, lowering the pH of the ocean waters. All right. With that, we're going to stop because that's depressing enough. All right. So next time, we're going to talk about the response to climate change. Again, there's so much what we could have talked about, but that's a general overview. Considering that the planet is 70% water, that's why we want to focus on ice, hydrosphere, ocean, that kind of thing. All right, but there are clearly land impacts as well. So next time, we're going to talk about how we respond to climate change, what are some options. Then much farther down the road, we'll talk about policy, because that doesn't get anybody upset at all. So that's it for this week. Take care.